Chapter Trigonometric Series. Section A, Trigonometric Functions. 66. For the engineer, and especially for the electrical engineer, a perfect familiarity with trigonometric metric functions and formulas is almost as essential as familiarity with the multiplication table. To use trigonometric methods efficiently, it is not sufficient to merely understand trigonometric formulas enough to look them up when required. Instead, these formulas must be memorized and understood in both directions. This means that an expression similar to the left side of a trigonometric formula should immediately recall the right side, and an expression similar to the right side should immediately recall the left side of the formula. Trigonometric functions are defined based on the circle and the right triangle. Consider the circle in Figure 28, where the direction to the right and upward is considered positive, and the direction to the left and downward is considered negative. The angle alpha is measured counterclockwise from the positive horizontal line, labeled OA, as positive, and clockwise as negative. The projection S of the angle alpha divided by the radius is called the sine of alpha. The projection C of the angle alpha divided by the radius is called the cosine of alpha. The intercept T on the vertical tangent at the origin, labeled A, divided by the radius, is called the tangent of alpha. The intercept CT on the horizontal tangent at 90 degrees behind A, divided by the radius, is called the cotangent of alpha. Thus, in Figure 28, the sine of alpha equals S divided by R. The cosine of alpha equals C divided by R. The tangent of alpha equals T divided by R. The cotangent of alpha equals CT divided by R. Right triangle shown in Figure 29 with the angles alpha and beta opposite the sides labeled A and B respectively, and with the hypotenuse labeled C, the trigonometric functions are defined as follows. The sine of alpha equals the cosine of beta, which equals A divided by C. The cosine of alpha equals the sine of beta, which equals B divided by C. The tangent of alpha equals the cotangent of beta, which equals a divided by B. The cotangent of alpha equals the tangent of beta, which equals B divided by A. By using the right triangle, trigonometric functions can only be defined for angles up to 90 degrees, or pi divided by 2. However, by using the circle, trigonometric functions can be defined for any angle. Both representations must be so familiar to the engineer that they can visualize the trigonometric functions, their variations with changes in the angle, and, in most cases, their numerical values, simply from a mental picture of the diagram. 67. Signs of functions. In the first quadrant, as shown in Figure 28, all trigonometric functions are positive. In the second quadrant, shown in Figure 30, the sine of alpha remains positive because the projection labeled S is in the upward direction. The cosine of alpha becomes negative because the projection labeled C points toward the left. Both the tangent of alpha and the cotangent of alpha are negative because the intercept labeled T is directed downward, and the intercept labeled CT points toward the left. In the third quadrant, as shown in Figure 31, both the sine of alpha and the cosine of alpha are negative. In the third quadrant, as shown in Figure 31, both the sine of alpha and the cosine of alpha are negative. This is because the projection labeled S is downward, and the projection labeled C points toward the left. However, the tangent of alpha and the cotangent of alpha are positive, as observed from the intercepts labeled T and CT. In the fourth quadrant, as shown in Figure 32, the sine of alpha is negative because the projection labeled S is downward, but the cosine of alpha is positive because the projection labeled C points toward the right. The tangent of alpha and the cotangent of alpha are both negative, as seen from the intercepts labeled T and CT. In the fifth quadrant, all trigonometric functions have the same values as in the first quadrant, shown in Figure 28. This means that adding or subtracting 360 degrees, or 2 pi, or any multiple thereof, to the angle alpha does not change the trigonometric functions. These functions repeat every 360 degrees, or 2 pi, which is their period. Signs of trigonometric functions. 1. The sine of alpha is positive in the first and second quadrants and negative in the third and fourth quadrants. 2. The cosine of alpha is positive in the first and fourth quadrants and negative in the second and third quadrants. 3. The tangent of alpha is positive in the first and third quadrants and negative in the second and fourth quadrants. 4. The cotangent of alpha is positive in the first and third quadrants and negative in the second and fourth quadrants. 68. Relations between the sine of alpha and the cosine of alpha. The relation between the sine of alpha and the cosine of alpha is given by the square of the sine of alpha plus the square of the cosine of alpha equals 1. From this, the following can be derived. The sine of alpha equals the square root of 1 minus the square of the cosine of alpha. The cosine of alpha equals the square root of 1 minus the square of the sine of alpha. This equation is frequently used in both directions. For example, 1 may be substituted for the sum of the squares of the sine of alpha and the cosine of alpha. Conversely, the sum of the squares of the sine of alpha and the cosine of alpha may be substituted for 1. For instance, 1 divided by the square of the cosine of alpha equals the sum of the squares of the sine of alpha and the cosine of alpha divided by the square of the cosine of alpha. This simplifies to the square of the tangent of alpha plus 1. Relations between sines and tangents. The tangent of alpha equals the sine of alpha divided by the cosine of alpha. The cotangent of alpha equals the cosine of alpha divided by the sine of alpha. From this it follows the cotangent of alpha equals 1 divided by the tangent of alpha. The tangent of alpha equals 1 divided by the cotangent of alpha. Since the tangent of alpha and the cotangent of alpha are less convenient for trigonometric calculations compared to the sine of alpha and the cosine of alpha, they are less frequently used. It is not necessary to memorize trigonometric formulas related to the tangent of alpha and the cotangent of alpha. Instead, wherever these functions appear, they can be expressed in terms of the sine of alpha and the cosine of alpha using the previously mentioned equations. Calculations can then be carried out with the sine and cosine and the tangent or cotangent of alpha resubstituted into the final result if it contains the sine of alpha divided by the cosine of alpha or its reciprocal. In electrical engineering, the tangent of alpha or the cotangent of alpha frequently appears as the starting point for calculating the phase angle in alternating current systems. For example, if alpha represents the phase angle of a vector. The tangent of alpha is defined as the ratio of the vertical component to the horizontal component, or equivalently, the ratio of the reactive component to the power component. If the tangent of alpha equals a divided by b, then the sine of alpha equals a divided by the square root of the sum of a squared and b squared, and the cosine of alpha equals b divided by the square root of the sum of a squared and b squared. Alternatively, if the cotangent of alpha equals c divided by d, then the sine of alpha equals d divided by the square root of the sum of c squared and d squared, and the cosine of alpha equals c divided by the square root of the sum of c squared and d squared. The secant and versed sine functions are rarely used in engineering and are generally considered mathematical curiosities. These functions are defined by the following equations. The secant of alpha equals 1 divided by the cosine of alpha. The cosecant of alpha equals 1 divided by the sine of alpha. The sine versed alpha equals 1 minus the sine of alpha. The cosine versed alpha equals 1 minus the cosine of alpha. 69. Negative angles. From the circle diagram of trigonometric functions as shown in figure 33, when changing from a positive angle represented by counterclockwise rotation to a negative angle represented by clockwise rotation, the directions of S, T, and CT are reversed, but C remains unchanged. This results in the following relations. The sine of negative alpha equals the negative sine of alpha. The cosine of negative alpha equals the positive cosine of alpha. The tangent of negative alpha equals the negative tangent of alpha. The cotangent of negative alpha equals the negative cotangent of alpha. Thus, the cosine of alpha is classified as an even function, while the sine, tangent, and cotangent of alpha are classified as odd functions. Complementary angles. From the circle diagram of trigonometric functions as shown in figure 34, when changing from an angle to its supplementary angle, the projection labeled S remains in the same direction, while the projections labeled C, T, and CT reverse their direction. All four quantities retain the same numerical values. This results in the following relationships. The sine of pi minus alpha equals the positive sine of alpha. The cosine of pi minus alpha equals the negative cosine of alpha. The tangent of pi minus alpha equals the negative tangent of alpha. The cotangent of pi minus alpha equals the negative cotangent of alpha. Charge complementary angles. When changing from an angle alpha to its complementary angle, represented as 90 degrees minus alpha or pi divided by 2 minus alpha, the signs of the trigonometric functions remain the same. However, the projections labeled S and C, as well as T and CT, exchange their numerical values. This leads to the following relationships. The sine of pi divided by 2 minus alpha equals the cosine of alpha. The cosine of pi divided by 2 minus alpha equals the sine of alpha. The tangent of pi divided by 2 minus alpha equals the cotangent of alpha. The cotangent of pi divided by 2 minus alpha equals the tangent of alpha. Angles alpha plus or minus pi. Adding or subtracting pi to an angle alpha results in trigonometric functions with the same numerical values as those for alpha, as shown in figure 36. However, the direction of the projections labeled S and C is reversed, while the directions of T and CT remain unchanged. This results in the following relationships. The sine of alpha plus or minus pi equals the negative sine of alpha. The cosine of alpha plus or minus pi equals the negative cosine of alpha. The tangent of alpha plus or minus pi equals the positive tangent of alpha. The cotangent of alpha plus or minus pi equals the positive cotangent of alpha. Stark angles alpha plus or minus pi divided by 2. Adding pi divided by 2, or 90 degrees, to an angle alpha interchanges the trigonometric functions associated with S and C, as well as T and CT. Additionally, their directions are reversed. Adding pi divided by 2, or 90 degrees, to an angle alpha interchanges the trigonometric functions associated with S and C, as well as T and CT. It also reverses the direction of the cosine, tangent, and cotangent, but leaves the sine unchanged. This is because the sine remains positive in the second quadrant, as shown in figure 37. Subtracting pi divided by 2, or 90 degrees, from an angle alpha also interchanges the functions S and C, as well as T and CT, and reverses their direction, except for the cosine, which retains the same direction. This occurs because the cosine remains positive in the first and fourth quadrants, as shown in figure 38. The relationships are as follows. The sine of alpha plus pi divided by 2 equals the positive cosine of alpha. The cosine of alpha plus pi divided by 2 equals the negative sine of alpha. The tangent of alpha plus pi divided by 2 equals the negative cotangent of alpha. The cotangent of alpha plus pi divided by 2 equals the negative tangent of alpha. The sine of alpha minus pi divided by 2 equals the negative cosine of alpha. The cosine of alpha minus pi divided by 2 equals the positive sine of alpha. The tangent of alpha minus pi divided by 2 equals the negative cotangent of alpha. The cotangent of alpha minus pi divided by 2 equals the negative tangent of alpha. Numerical values of trigonometric functions. From the circle diagram in figure 28 and similar diagrams, the following numerical values are obtained. The sine of 0 degrees equals 0. The cosine of 0 degrees equals 1. The tangent of 0 degrees equals 0. The cotangent of 0 degrees equals infinity. The sine of 30 degrees equals 1/2. The cosine of 30 degrees equals 1/2 times the square root of 3. The tangent of 45 degrees equals 1. The cotangent of 45 degrees equals 1. The sine of 45 degrees equals 1/2 times the square root of 2. The cosine of 45 degrees equals 1/2 times the square root of 2. The tangent of 90 degrees equals infinity. The cotangent of 90 degrees equals 0. The sine of 60 degrees equals 1/2 times the square root of 3. The cosine of 60 degrees equals 1/2. The tangent of 135 degrees equals -1. The cotangent of 135 degrees equals -1. The sine of 90 degrees equals 1. The cosine of 90 degrees equals 0. Additional numerical values follow similarly for other angles, such as 120 degrees and beyond. These values repeat periodically based on the trigonometric functions. 71. Relations between two angles. The following relations between two angles alpha and beta are commonly developed in textbooks. If the sine of alpha plus beta equals the sine of alpha multiplied by the cosine of beta plus the cosine of alpha multiplied by the sine of beta. The sine of alpha minus beta equals the sine of alpha multiplied by the cosine of beta minus the cosine of alpha multiplied by the sine of beta. The cosine of alpha plus beta equals the cosine of alpha multiplied by the cosine of beta minus the sine of alpha multiplied by the sine of beta. The cosine of alpha minus beta equals the cosine of alpha multiplied by the cosine of beta plus the sine of alpha multiplied by the sine of beta. From these equations, the following relationships can be derived by combining the equations in pairs. The product of the cosine of alpha and the cosine of beta equals 1/2 the sum of the cosine of alpha plus beta and the cosine of alpha minus beta. The product of the sine of alpha and the sine of beta equals 1/2 the difference between the cosine of alpha minus beta and the cosine of alpha plus beta. The product of the sine of alpha and the cosine of beta equals 1/2 the sum of the sine of alpha plus beta and the sine of alpha minus beta. The product of the cosine of alpha and the sine of beta equals 1/2 the difference between the sine of alpha plus beta and the sine of alpha minus beta. By substituting alpha sub 1 for the sum of alpha and beta beta sub 1 for the difference between alpha and beta in these equations, the following equations are obtained. The sine of alpha sub 1 plus the sine of beta sub 1 equals 2 times the sine of the average of alpha sub 1 and beta sub 1 multiplied by the cosine of half the difference between alpha sub 1 and beta sub 1. The sine of alpha sub 1 minus the sine of beta sub 1 equals 2 times the sine of half the difference between alpha sub 1 and beta sub 1 multiplied by the cosine of the average of alpha sub 1 and beta sub 1. The cosine of alpha sub 1 plus the cosine of beta sub 1 equals 2 times the cosine of the average of alpha sub 1 and beta sub 1 multiplied by the cosine of half the difference between alpha sub 1 and beta sub 1. The cosine of alpha sub 1 minus the cosine of beta sub 1 equals -2 times the sine of the average of alpha sub 1 and beta sub 1 multiplied by the sine of half the difference between alpha sub 1 and beta sub 1. These three sets of equations are some of the most important trigonometric formulas. Memorization can be made easier by noting the following patterns. Cosine functions lead to products of equal functions, while sine functions lead to products of unequal functions. Conversely, products of equal functions resolve into cosine functions, and products of unequal functions resolve into sine functions. Cosine functions also show a reversal of the sign. The cosine of a sum is given by a difference of products, and the cosine of a difference is given by a sum of products. This behavior reflects the fact that as the angle increases, the cosine function decreases, so the cosine of a sum of angles is less than the cosine of a single angle. From the relationships for the sum and difference of angles, substituting alpha for beta gives the following double angle formulas. The sine of 2 times alpha equals 2 times the sine of alpha multiplied by the cosine of alpha. The cosine of 2 times alpha equals the square of the cosine of alpha minus the square of the sine of alpha. This can also be expressed as 2 times the square of the cosine of alpha minus 1, or as 1 minus 2 times the square of the sine of alpha. From these formulas, it follows that the square of the sine of alpha equals 1 minus the cosine of 2 times alpha divided by 2. The square of the cosine of alpha equals 1 plus the cosine of 2 times alpha divided by 2. 72. Differentiation. The derivative of the sine of alpha with respect to alpha equals the positive cosine of alpha. The derivative of the cosine of alpha with respect to alpha equals the negative sine of alpha. The negative sign for the latter derivative arises because as the angle alpha increases, the cosine of alpha decreases. Integration. The integral of the sine of alpha with respect to alpha equals the negative cosine of alpha. The integral of the cosine of alpha with respect to alpha equals the positive sine of alpha. From these, the definite integrals over a full period are the integral from c to c plus 2 pi of the sine of alpha plus a with respect to alpha equals 0. The integral from c to c plus 2 pi of the cosine of alpha plus a with respect to alpha equals 0. The following definite integrals hold true. The integral from negative pi divided by 2 to positive pi divided by 2 of the sine of alpha with respect to alpha equals 0. The integral from 0 to pi of the cosine of alpha with respect to alpha equals 0. 73. Binomial transformation. One of the most common trigonometric operations in electrical engineering is the transformation of a binomial expression involving trigonometric functions into a single trigonometric function. This is achieved by the substitution. Let A equal C multiplied by the cosine of P and B equals C multiplied by the sine of P. Then A multiplied by the cosine of alpha plus B multiplied by the sine of alpha equals C, multiplied by the cosine of the quantity alpha minus P. Here, C equals the square root of A squared plus B squared, and the tangent of P equals B divided by A. Alternatively, by substituting, let A equal C multiplied by the sine of Q and B equals C multiplied by the cosine of Q. Then A multiplied the cosine of alpha plus B multiplied by the sine of alpha equals C multiplied by the sine of the quantity alpha plus Q. Here, C equals the square root of A squared plus B squared, and the tangent of Q equals A divided by B. 74. Polyphase relations. The sum of I multiplied by the cosine of the angle alpha plus A plus or minus 2 times m times I times pi divided by n over all I from 1 to n equals 0. The sum of I multiplied by the sine of the angle alpha plus A plus or minus 2 times m times I times pi divided by n over all I from 1 to n also equals 0. Here, m and n are integers. Proof. The points on the circle corresponding to the trigonometric functions of the angles alpha plus A plus or minus 2 times I times pi divided by n, as depicted in figure 28. The points corresponding to the angles alpha plus A plus or minus 2 times m times I times pi divided by n, where I ranges from 1 to n, represent the vertices of a regular polygon inscribed in the circle as shown in figure 39. The center of the circle is also the center of gravity of this polygon. For example, when n equals 7 and m equals 2, the vertices are labeled as P1, P2, up to P7 in figure 39. The cosines of these angles correspond to the vertical projections of the vertices, while the sines correspond to the horizontal projections. Since the sum of the projections of the vertices of any polygon on any line passing through its center of gravity is equal to 0, the sums of the sines and cosines in equation 23 are 0. Additionally, the following relationships hold: the sum over I from 1 to n of I multiplied by the cosine of alpha plus A plus or minus 2 times m times I times pi divided by n, multiplied by the cosine of alpha plus B plus or minus 2 times m times I times pi divided by n equals n divided by 2, multiplied by the cosine of A minus B. The sum over I from 1 to n of I multiplied by the sine of alpha plus A plus or minus 2 times m times I times pi divided by n, multiplied by the sine of alpha plus B plus or minus 2 times m times I times pi divided by n equals n divided by 2, multiplied by the cosine of A minus B. The sum over I from 1 to n of I multiplied by the sine of alpha plus A plus or minus 2 times I times pi divided by n, multiplied by the cosine of alpha plus B plus or minus 2 times m's I times pi divided by n equals n divided by 2, multiplied by the sine of A minus B. These equations are proven by replacing the products of trigonometric functions with single trigonometric functions using equations 14 and substituting these results into equations 23. 75. Triangle. In a triangle, let the angles alpha, beta, and gamma be opposite the sides labeled A, B, and C, respectively, as shown in figure 40. The following relationship applies. The 75. Triangle. In a triangle, let the angles alpha, beta, and gamma be opposite the sides labeled A, B, and C, respectively, as shown in figure 40. The following relationship applies. The sine of alpha divided by the sine of beta divided by the sine of gamma equals A divided by B divided by C. Alternatively, in a triangle, the following relationships hold. The cosine of gamma equals the square of side A plus the square of side B minus the square of side C, all divided by 2 times A times B. The square of side C equals the square of side A plus the square of side B minus 2 times A times B, multiplied by the cosine of gamma. Section B. Trigonometric series.